In this video lecture, we're going to discuss context-free grammar. So as just a review of our last video lecture, we discussed the different types of grammar based on Chomsky, and also we discussed type 0, which is the regular grammar, wherein we know that regular grammar produces regular language and it could be accepted by finite automata. Okay? And context-free grammar is type 1. So what is the difference between the two? So regular grammar is either right or left linear, whereas context-free grammar is basically any combination of terminal and non-terminal. So therefore, you can see that regular grammar is a subset of context-free grammar. Type 0 is part of type 1 grammar. So all regular grammar could be considered as context-free grammar. So now, let's discuss context-free language, which is the language created by context-free grammar. So again, context-free language are generated by context-free grammar. So the set of all context-free languages is identical to the set of language accepted by push-down automata. So push-down automata is different from finite automata finite automaton. Push-down automata is the one that accepts context-free language, which is generated by context-free grammar. So again, all regular languages are context-free grammar, or free language rather, but not all context-free languages are regular. Don't forget, CFL is bigger than RL. So all RL are CFL, but not all CFL are RL. Okay? Don't forget that. And also, CFL are used in computer science, in natural language processing, and computer language design. So that's some of the application of CFL. So now let's move on go back rather, with context-free grammar. So context-free grammar could be defined formal. Definition will be represented by the for tuple. So we have grammar will be represented by the terminal symbol, which is V, and the non-terminal symbol, which is represented by sigma, and S again for start symbol, and P for the production rule that will define how we're going to generate the strings. Okay, and as you can see here in the production rule, so compare with the regular language, context-free grammar for the production rule, it has an asterisk, so therefore it could be present or not with regards with the transition. Okay, so it includes epsilon. So let's have this example. So for generating a language that generates equal number of A's and B's in the G in the form of A raised to N, B raised to N. So the context-free grammar will be defined as, this is the production rule. And going back to our previous discussion about non-regular and regular, as you can still remember, A raised to N, B raised to N is not a regular language, okay? Because we cannot count the number of A equal to the count of number B using finite automaton, okay? So it cannot be accepted. But in context-free grammar, it could be generated. It could be accepted by push-down automaton. So as you can see, going back to our previous slide, previous slide, I said that regular languages are all part of context-free grammar, and context-free grammar is not all regular language. This is the example of this. A raised to N, B, and N is not regular, but context-free grammar. Okay? So let's have again this grammar. So the non-terminal symbol are S and A, terminal symbol, small a, small b, and our production rule. As you can see with the production rule, so start yields to small a, capital A, and B. As you can see here, so this could be either considered as light or ref align. So we have a um, close terminal symbol on both sides. So it could be not be considered as left or right. So this is the difference between the regular grammar. Okay, and we also have this. Okay, for A. So let's start generating our symbol or our string. So we're going to start with the start rule. So start symbol is S, wherein it will yield to small a, capital A, and B. And we all know, based on the second rule, we could replace A, capital A, by small a, capital A, and B. So therefore, this A could be replaced by these three letters. And same rule could be applied to replace A to introduce another this small a, capital A, and B to our string. And again, same rule, which is the second, could be implemented to replace A. So now we have four A's and four B's. And on the same rule, it could be A could be replaced by an empty symbol, which is epsilon. So therefore, A could be removed. So we have four A's, four B's. So now, what can you say about the number of A's and B's? So based on the rule, we are assured that number of A's will be the same as B. Okay, so in this example, we have A raised to 4, B raised to 4. So we have 4 A's, B, 4 B's. And if we're going to consider the third line, as you can see here, we have 3 A's and 3 B's. On the second line, we have 2 A's and 2 B's. So again, based on the production rule, we are assured that we have the same length for A and B's. So this string is accepted based on the given rule. Okay, so going back to regular language, we cannot do that. But in CFG, we could determine that this string is accepted. Okay, so that will be our last slide for this video lecture. See you on the next continuation of CFG. Thank you for listening.